And welcome to Climate Chat. I am your host, Dan Miller, and today our special guest is Eric Rignot. And I'm trying to say it right. and I've actually, Eric, I've been following you for a long, long time, and I'm including your information in my climate talks like a long time ago. So it's really great to have you here. Eric is a glaciologist and climate scientist who is studying some of the most important work on the planet right now that actually is not being discussed enough. So I'm really happy to have you on here. I'll just give a very brief background. I'm going to ask you a little bit more about your background. But Professor Rignot is a world-renowned glaciologist who studies the effect of global climate change on polar ice sheets. He uses satellites, airborne sensors, field data, and numerical models to understand the dynamics of glacier ice along the coast of Antarctica and Greenland ice sheets, as well as in Alaska and Patagonia. His research has documented major acceleration of ice loss as a result of climate change and has been widely covered in the media. In addition to his appointment at University of California at Irvine, he is a senior research scientist at NASA's Jet Propulsion Laboratory, JPL, where he leads several NASA-funded projects. So, Eric, welcome. I'm going to ask my first question is, tell us a little bit about more about your background and how do you become a glaciologist?
It's not a linear road to get there. So my training is in engineering. I got actually an engineer's degree in France. I followed the cursus of engineers, which doesn't go through the university in France. It goes through specialty schools. And then I moved to the US for graduate studies. I did aerospace engineering, electrical engineering, and I eventually landed a job at the Jet Propulsion Laboratory to work on synthetic aperture radar. I did not know much about that, but I was really interested in remote sensing. I had a background in electrical engineering. I started working on sea ice applications and drifted into glacier ice. I did some forestry. It took a little while before I sort of formed my sort of field of research, and things starting really kicking in nicely for me, being at the right time at the right place, doing the right thing at JPL when SAR interferometry became possible with the launch of the ERS-1 satellite. That was in 1991, 92. So my life took a different turn at that point, and I could not have predicted that.
Wow. By the way, I'm also got a degree in electrical engineering, and also my first job was designing satellites. So we have a little bit in common over there. I do want to jump right into sea ice and sea level rise and all of those things.
Yeah.
When we talk about sea level rise, we talk about Greenland. And then when we talk about Antarctica, we tend to talk about the West Antarctic ice sheet. Why is that? And why is the West Antarctic ice sheet so important?
Yeah, so and when you look at the map in Antarctica, it may not be obvious to you who is west, who is east, right?
Right.
There's no flag to tell you. So usually when you look at a map of Antarctica with the 0 degree longitude pointing to South Africa up, you see the Antarctic Peninsula on your left. And the West Antarctic is the part of the Antarctic towards your left side of the screen. And it's a part of Antarctica that's lower. The surface is lower than the rest of the Antarctic. It's also grounded on a bedrock that is mostly below sea level. So we call it a marine ice sheet. Whereas East Antarctica is sitting on a sort of larger continent that is mostly grounded above sea level, but not all of it is actually grounded above sea level. And the plateau of East Antarctica stands higher. So by tradition, glaciologists have viewed West Antarctica as more vulnerable to climate change. It's also lower, it sits in a warmer climate, and because it's resting on bedrock below sea level, if it melts, it wants to become a floating ice sheet, whereas East Antarctica will, in principle, be more resilient to climate change. But that's a story. We could talk more about that.
Okay, let's do that. But as we zoom in on West Antarctic ice sheet, there's a particular glacier called the Thwaites Glacier, which is
Yes.
nicknamed the Doomsday Glacier. Why is that?
Well, I did not nickname it the Doomsday
Okay.
Glacier. That was Rolling Stone magazine uh,
Okay.
who made this concept popular. Um, it's good on one side because it tells the readers, the public, this is sort of a danger uh, for the future, doomsday, the fact that this glacier could collapse to sea in the coming century. What I don't like about it is it seems to summarize the evolution of ice sheets in Greenland and Antarctica to a single glacier.
Hmm.
And that's overly simplistic. Thwaites Glacier is not the only glacier we're worried about. There are lots more, but it's in the limelight, right? It's a very large one. It is vulnerable to climate change, and it's been retreating rapidly in the past 40 years.
Okay. Well, kind of stepping back a little bit, all of the West Antarctic ice sheet. I've been giving climate talks for a long time, and I remember reading some things that you said quite a long time ago. I don't exactly remember how long, but I thought you were saying that we had passed the tipping point for the West Antarctic ice sheet. So my first question is, did I have that right?
Yes.
And what does the collapse of the West Antarctic ice sheet mean to us this century and beyond?
Yeah, so we have to go back a little bit in history, right? I was not the first person to point out at the vulnerability of West Antarctica. It goes back to the 1960s when
Wow.
Charlie Bentley crossed the West Antarctic. He was in his 20s back then with seismic recordings, and he discovered that the bed of that ice sheet was really deep below sea level, almost 2 kilometers below sea level. He spent actually 2 years in the field. He was not able to come back right away. And he spent a lot of time in the field trying to make sure that what he was doing was right. Right? As a scientist, you're always afraid that you made an error in your measurements. And he was right. And that was really surprising to people that the ice sheet could be grounded so far below sea level and still be around. In 1957, Johannes Wirtman, another glaciologist, published a paper that suggested that an ice sheet resting on a bedrock like this, deep below sea level, with a slope getting deeper in the inland direction, was not stable unless it reaches the edge of the continental shelf. Otherwise, if it's not at the edge of the continental shelf, it should not be around. So people starting worrying about why is West Antarctica even there? And other glaciologists such as Bob Thomas and Terry. I forget his name. Terry Hughes.
Okay.
Terry Hughes hypothesized that the most vulnerable part of West Antarctica was the Pine Island Thwaites sector. And Terry Hughes back then, that was the 70s, then even put forward the concept that maybe this part of Antarctica was already in a state of collapse. We did not have much evidence for that. In fact, Charlie Bentley himself had evidence contrary to that at some point, until the 1990s, when we had SAR interferometry. We also had altimetry data that showed that there was something big happening in this sector. We didn't know how long it had been going on, but the glaciers were changing in a major way. And like Terry used to tell me back then, he said, nobody believes me until Eric shows up with his data, and then they Eric. So I get no credit for that.
Okay.
But I sort of, when I look at interferometry data on these glaciers, was not by chance. I was aware of his theories that this was the most important part of the Antarctic, and no one was actually in the field. No one was studying them. most of the Europeans were working on the Filchner-Rodney ice shelf in the field, and the Americans were working on the Cyprus Coast ice stream on the Ross Sea. The Amundsen Sea sector was a no man's land. So we had to have this satellite data to stumble on what was going on at that time. So it goes way back.
Yeah.
It goes way back. And around the same time, physical oceanographer from the Lamont Observatory, Stan Jacobs, and his colleague, Adrian Jenkins from the British Antarctic Survey, came back from a ship expedition and discovered there was a lot of warm water in front of the glaciers. That was not expected. Again, we did not know whether this was new or as always the case. That was consistent with the data that I had that showed very rapid melt of the glaciers in the ocean. But there was still a lot of unknowns about this area. There were maybe a couple of flight lines on radar thickness. So the international community started to get together to collect more data in this environment, which was a bit of a challenge. The first big expedition was a NASA Chilean venture, which launched about two or three expeditions starting from South America. We flew from Punta Arenas all the way to West Antarctica, collect data, and came back. That was exciting. Nobody thought it was possible, and proved it was possible. And then University of Texas, British Antarctic Survey came back for more data. And then NASA came back with Operation Icebridge. I don't know if you heard about that. It started in 2009. For about 10 years, we flew a lot of airborne surveys in this area. And so at that point, around 2014, I think we had enough description of the bed of this area. We had, of course, more satellite information on this sector. And it really looked like we were in the framework was that of a marine ice sheet instability. The glaciers were retreating fast. The bed was getting deeper inland. And at that point, I think we made the claim. We think that this system is on the course of unstoppable retreat. We don't see much in our data, and we've been looking for all these past years. We don't see much that could stop the retreat from going all the way to the deep subglacial trench that Charlie Bentley discovered in the 60s behind Thwaites, 2 kilometers below sea level. John Wertmann is right. Bob Thomas is right. Once you start pushing these glaciers, they start retreating. It's really hard to stop them. So that was 10 years ago. I don't think my mind has changed on that. The question is more, the trillion-dollar question for this area is just how fast could these glaciers retreat? And that we don't know.
Well, let's take a look at it like maybe from you're an insurance manager. You're looking at risk. And you want to know, maybe what the average time is of all the estimates. But I also want to know what's the 95%, the 5% probability number. Like how fast is possible? Yes. And then how slow, I guess I'd also want to know. But what if it was as bad as it could be? Are we talking about 10 or 20 years? Or are we talking about 100 or 200 years? Or
yeah, that's a very good question, Dan. I've been wondering about that for the past 30 years, and I don't have the answer. So as of now, Thwaites is retreating about, it depends exactly what you're looking at, but 0.5 kilometer to 1 kilometer per year. That's very fast, right? Alpine glaciers retreat at kilometers per century. Kilometer per year is sort of the fastest rate of retreat on the planet. In Greenland, the most worrisome glaciers retreat about 0.5 kilometer per year. So in Antarctica, we beat that. But we know that in the past, ice sheets have been able to change even more rapidly than that. So 1 kilometer per year, I would say it's just the beginning. We just don't know how much faster it could go. So I'll give you
Well, how many kilometers before it passes the grounding line?
Well, so for the grounding line to retreat through the whole basin at that rate, within 100 years, a lot of it will be gone. That's sort of the scale. To make this happen within 10, 20 years, I don't think is realistic.
Okay. Well, that's good.
But we don't know. You see, the problem with this marine ice sheet instability, we've seen some on the glacier level for instance, in Alaska. There was Austin Post, a glaciologist in Alaska who studied the evolution of Tidewater Glacier, and he was a photographer, but very smart observer. He figured out the tidewater cycle. When glaciers were retreating in the deeper bed, the retreat was rapid and unstoppable. It's exactly the same concept as the marine ice sheet instability. But we've never seen, as scientists, an ice sheet collapse. We have no idea how fast it could go. We know that 14,000 years ago, sea level rose 4 times faster than it is today, 4 meters per year, 4 meters per century. Sorry,
4 meters per century, which is that's a lot.
That's a lot.
That would 1 meter is a lot.
That's sort of the big worry we have is we know ice sheets could do that. How do they do that is a little bit a question mark. We haven't quite put our finger on it. I want to mention this recent paper that came out from Oshvat et al. Looking at the glaciers in the Antarctic Peninsula, which have been collapsing, and we kind of paid attention to it and not, because they're little glaciers, and the peninsula, for the purist, is not Antarctica. It's just that little finger that sticks out towards South America. But they just showed, the Larsen B ice shaft, collapsed in 2002. Made it in Hollywood, a big feature movie. It was a spectacular collapse because it progressed for decades, but suddenly in 3 weeks, the whole ice shaft collapsed and the glacier sped up. We sort of thought the thing could potentially die out, but in the last 3 years, these glaciers collapse even faster than we've ever seen before, and they retreated 8 kilometers per year.
Wow.
So I see these studies, and it gives me a little jolt, a little warning that we should be very careful not to be too conservative about how fast some of these glaciers could retreat. The glaciers in the peninsula are doing this right now, 8 kilometers per year. So that's a much bigger threat if this happens on Pine Island and Thwaites Glacier. And then
but again, because of the distance involved, you're saying at a kilometer a year, maybe it's 100 years, but if it was going at 4, then is it 20, 30 years?
10 kilometers per year. I would have to look at my map. I haven't done the exercise. I've never dared imagine that these glaciers could retreat that fast. So I don't know, but certainly within this century.
Okay, well, that's a big deal. And by the way, so let's talk about it. Let's say it does, well, when it happens, because it's like inevitable, but if it's this century, next century, and it collapses, how much does that contribute to global sea level rise?
So Thwaites and Pine Island, they are brothers and sisters, hold a potential sea level rise of 1.2 meters.
Okay.
But
so about 4 or 5 feet.
Yeah. But if they collapse, they will trigger the collapse of the rest of West Antarctica. They will sort of eat the rest of West Antarctica from behind. Instead of the frontal section of the rest of West Antarctica collapsing, they will be collapsing from behind. And that's a 3-meter potential sea level rise from West Antarctica.
12, 14 feet. Okay. And speaking of all of this, there's a lot of talk about the AMOC, the Atlantic Meridional Overturning Circulation, shutting down. A lot of predictions now, mid-century beginning of the shutdown. And Jim Hansen has said that when that happens, the warm water that was going to Europe is going to hang around Antarctica and speed up melting. Because one thing we didn't say, but you've certainly talked about in your talks, is the melting is occurring from below, from the ocean water, not from heat. People think of the sun shining on Antarctica and
That's
melting it. No, it's coming from below. So what are your thoughts on that, the scenario of AMOC shutdown, keeping warmer water towards Antarctica, accelerating that even further?
Well, I am concerned about that. I'm also concerned about the fact there's a little bit of focus on AMOC, but the sort of bigger part of the thermoline circulation, the global thermoline circulation of heat and nutrients around the planet, is really centered around the Antarctic. The AMOC, the North Atlantic circulation, is just one of the branches. There's a branch, Pacific, Indian Ocean, but around the Antarctic, the ocean circulation goes all around Antarctica. There's no piece of land that prevents the ocean to circulate clockwise when you look at South Pole around the Antarctic. And that circulation could also be perturbed independent of what's happening in the North Atlantic, because the sea ice is collapsing since 2016.
Right,
because
I was going to ask you about that later.
It's warming. There's a lot of things changing. The ice sheet melting. We've not paid a lot of attention to the Southern Ocean circulation. AMOC is a concern, and Jim is right. The AMOC slowing down could perturb the Antarctic, but that heat takes a long time to circulate through that loop. It typically takes 1,000 years for a particle of water to do the whole loop. So it's not necessarily clear that the impact of the AMOC will be dramatic and immediate on the Southern Ocean. Meantime, I'm concerned about what the Southern Ocean is doing itself, and we don't have a lot of observations for that. And there's a recent article by Neroli Abrams in Nature discussing that. It's more focused on the Antarctic, that there's a lot of renewed interest in understanding what's happening in the Antarctic. It's changing rapidly.
So as the sea, so the folks who don't know, the Antarctic sea ice is not land ice. It's it's sort of ice in the ocean around Antarctica, and in recent decade or so, it's been going through dramatic changes where it's actually gone to record highs and record lows, and now it's at a record low. And my understanding of tipping points, of what you see before a tipping point, is you see a big oscillation in something before it hits a systemic shift. Do you think that kind of thing is going on here? And
well, it's we don't know. There's still a little bit of debate on how to explain what is happening here. The strength, the winds in the Antarctic have been getting stronger. The westerlies have increased, and when they increase, they also tend to contract towards Antarctica. And that increase in the westerly is well understood from basic physical principle. The Antarctic is not warming as fast as the rest of the planet. The ozone hole is also contributing to a little bit of cooling. So the sort of temperature differential between the Antarctic and the rest of the world has not reduced. It's increased a little bit. The winds get stronger, and that tends to push the surface waters northwards. That's Ekman transport. That's the Coriolis effect. That helps the sea ice expand a little bit, which has been doing for the past 4 years. It expands very slowly, 1% per decade. And conversely, when you expand the surface waters, you bring the bottom waters closer to the continent, and that's the warm water that melts the ice, and you cannot see with the naked eye, like you pointed out. All of that stuff is happening well below the surface.
But when the sea ice is gone, as at record low, I would also assume the sun energy is being absorbed right around Antarctica, more so than it normally would, right? If otherwise the ice would reflect it away. Does that contribute to the melting of West Antarctica and other places?
So for the sea ice, everything contributes. The ocean circulation, the winds are very important. and the surface climate. It seems that the Antarctic sea ice has reached a breaking point. It's expanding less, and then the warming is starting to catch up with it. Uh, so since 2016, we saw this dramatic reduction in sea ice in the Antarctic. I mean, it's comparable to the retreat of Arctic ice over 40 years in 10 years. So it's quite dramatic. And that has a big influence on the Southern Ocean, a big influence on the thermal line circulation. And it's a very rapid signal. Call it a tipping point. It's more like a big surprise.
Okay.
And a big signal that
not a good surprise.
Not a good surprise. It's especially staggering to see how fast that transition occurred. The initial paper by Claire Parkinson at Goddard was in 2018, and she was like, something is going on. I don't know if it's going to carry on, but something big is carrying on. And the record is extending to see a dramatic reduction of sea ice in the Antarctic.
Now, Antarctica gets a lot of attention, such as the big place where most of the ice is, but Greenland is melting really fast and contributing a lot to sea level rise, but also to putting fresh water in the North Atlantic, which is the thing that's going to trigger an AMOC shutdown. What can you tell us about the rate of Greenland melting, its contribution to sea level rise, and that kind of thing?
Well, so first on the impact of Greenland on the AMOC. Well, it's not just Greenland. Well, fresh water comes from Greenland melt, from snow melt, from river discharge, all of these features. But my sort of understanding of that, but there's a wide literature on the topic, is that you need a lot of fresh water dumping into the ocean to really shut down the AMOC, and we're nowhere close to that. But there are also studies that suggest that the AMOC could slow down in proportion to the amount of fresh water that we dump in the North Atlantic, meaning it's not an on and off thing. It could be also AMOC slowing down over time.
Well, which of course it is already.
Yeah. But
by the way, on that thing about there's not enough fresh water, Jim Hansen says actually the IPCC or whatever models are using don't have ocean mixing correct, and that's why they think it needs a lot more. And he says it's more sensitive to the fresh water than those models suggest.
It could be. I mean, I would say we have to be very cautious about that. We have observations, we have models. We know the AMOC changed rapidly in the past, so we don't have all the answers at this time to say we should not worry or we should worry about it tomorrow. It remains a topic of research.
Well, of course, it's also an existential threat. So maybe I would say let's assume the worst and hope for the best. But just how about Greenland, though, and its contribution to sea level rise this century? How can you bound that one with the 5%, 95% kind of numbers?
Yeah, so Greenland is in contrast to Antarctica, it's melting everywhere.
Right.
Antarctica is just a few pockets that are changing, but Greenland, all the glaciers are spinning up. There's melting at the surface that increases, so it's the surface climate. It's the ocean eating the glaciers. But the difference with the Antarctic is that a lot of the glaciers in Greenland eventually will retreat above sea level, except in the north. So that's why I'm actually more concerned about what's happening in the north of Greenland than in the south, because the north hosts marine-based glaciers. And Jakobshavn and the northern glaciers hold together a 3-meter potential sea level rise.
Wow.
They convey the concept of marine ice sheet instability because they stay below sea level all the way to the center of Greenland. So I'm a bit worried about these ones, even though at present they're not the largest contributor to sea level, right? So what we learn in the Antarctic is relevant to Greenland and vice versa, where it's important to to see the evolution of the glaciers in both places. Right now, Greenland is the big player, but the potential sea level rise from Antarctica is way bigger.
In the long run, but this century. So one thing I heard actually again from Jim Hansen was that, and this was maybe 5 years ago. So, but there was a doubling rate of ice loss from Greenland, and it was in the 5 to 10 year, like every 5 years it doubled. Is that
Yeah.
leveled off? Because if it
Yes.
doesn't level off, you can actually do a pretty good prediction of what the sea level is going to be, even if it's only 1 millimeter a year today. By the end of the century, at any doubling rate, you're up into the meters, right? So
Yeah, so that doubling depends on the length of the record you're looking at then. So if you look at the last 20 years,
Yeah.
which has been really well monitored by the GRACE mission using gravity data, you look at the entire record now, and things are not accelerating that much on average. It's pretty linear. If you include the record that extends back to 1980, then you see a lot more curvature in that profile. We may be in a linear part of the system, but it started off at a quadratic. So Jim refers to that longer record rather than the GRACE record. The GRACE record would tell you, well, it's steady, right? It's melting away, but it's no acceleration.
Which is not good, but it's not as bad as if it was doubling every 5
longer
years.
record is more important. You cannot look at climate with 20 years. You want sort of century scale data to say much about this.
Although as things change, like you just talked about the West Antarctic ice sheet. I mean, there's processes happening now that could play out in 20 years, which never happened before, right? So it's both a long-term view as well as for these big changes that can happen actually in a blink of an eye from
Absolutely. It's the mix of the long-term trend and the natural variability that you need to always worry about when interpreting the data, especially short records.
So can you give us just an overall feeling for what you think sea level rise this century might be contributed by both Greenland, actually all the glaciers, and land glaciers as well?
Well, my view hasn't changed in the last sort of 10, 15 years about this. I think we're on course for a meter sea level rise per century right now. But we cannot exclude that it could speed up from that in the second part of the century. We really don't know enough at that point to tell insurance companies, for instance, that they should really worry about what's going to happen in 2060 or 2080. It also depends on what we're doing collectively on the planet in terms of curbing our greenhouse gas emission and things like that.
Which we haven't done.
Well, we're working on it. I think there's some, the last COP meeting had some sort of signs of hopes, but we're not doing it fast enough.
Yeah, that's for sure. So, well, tell us what's your latest research? What's the latest things you're working on, and what does that tell us about the state of the planet?
Yeah, so I'm spending a lot of time looking at the grounding line these days because we have a new satellite data which I never had before that come almost daily and show us things in more detail. And we realized that the seawater is able to go underneath the glaciers over much larger distances than we thought initially. In principle, the models assume that seawater during the tidal cycle can go underneath the ice as it's being lifted up and down over a few hundred meters. And what we find is the real distance is more like kilometers. And that makes the glaciers more sensitive to a warming of the ocean water. Some pioneer modeling studies 10 years ago suggested by Byron Pyrezek and others suggested if there is something like this happening, kilometer scale intrusion of water underneath the ice. And we don't know if it's true, but some of the radar data we have showing the strength of the echoes under the ice suggests it could be. They run this into their models, and they found that the glaciers are more sensitive, and they lose mass more rapidly. And overall, you could almost double the contribution of these glaciers to sea level rise.
So,
And there's been subsequent studies with more sophisticated models that agree with that. But now we have the evidence that, yes, there is indeed intrusion of water very far underneath the glacier. And the melt rates are the highest where it hurts the glaciers the most. And none of that is really in the IPCC class of models. The IPCC class of models say, you have a strong boundary at the junction with the ocean. This is the grounding line here, and it's not moving up and down. It stays there, and at the grounding line itself, there should be no melt.
right.
And what we found, because of this constant flushing of seawater underneath the glaciers, there's actually a lot of melt right where it hits the glaciers the most, because it can eventually detach the glacier from the bed. It doesn't feel friction, and then the glacier can speed up.
Mm-hmm. Mm-hmm.
So we're spending time on this, looking at the satellite data, making sure we understand it correctly, putting some expeditions together to go explore this environment, because we've never explored any of these places, to try to understand it better.
So even a meter of sea level rise is catastrophic, but 2 meters is even more. And any thoughts of how much we could see in 2050, 2060? Is there any limit? Like, the most we could see is this, or the least we'll see is that?
Yeah, so currently the most models don't show any sort of tipping point happening, in the coming 25 years. In these models, things start to fall apart a little bit more in the later part of the century. But what do we know? One thing I'm working on a lot with my research group also is to make sure these models are able to match the observational record, which is now 40 years long. And most of them struggle to do that. So if they struggle to do that, why should we trust them to predict the next 40 years? So we're sort of working on that. And on Thwaites, we have a working model, and it makes projections that fall in the range of IPCC projection. But the IPCC projections are typically very broad. Right?
Sure, of course.
The range is enormous. And now we narrow it down. And the numbers are not scary, right? They're reasonable. But our model does not account for rapid calving of floating ice shelves that we see in the peninsula that was just revealed in the last few years. We don't have
you
that.
actually see that you're seeing it, and they're not predicted, right?
Yeah, so it still remains a conservative model of
Sure.
how things could change. I would say this is the model based on what we've seen so far, but it could be shattered a little bit if suddenly, like in the peninsula, we see glaciers going through these domino effects where the ice shelf suddenly falls apart very quickly. It's not continuum mechanics anymore. It's fracture mechanics. It makes the modeling far more complex, and that's sort of the next line of research. Right? I mean, the focus of researchers should really be to project the worst case scenario, because that's what we care about for sea level, not the conservative scenario or business as usual, but just how bad could it be? Because that's what's going to count for flooding of the coastline, just how bad it's going to be, right?
Well, it's what you should prepare for, right? I mean, it hopefully won't get that. Maybe we have a little more time than it could be, but it's going to be there eventually, by the way, right? There's nothing going to stop it. Well, speaking of that, what can we, is there anything that we can do to stop it? You mentioned lowering emissions. Well, we might lower emissions a little bit. We're not lowering them dramatically. I've seen things about putting curtains up around these glaciers to try to prevent them from any crazy schemes like that you've looked at that are actually possible.
So the geoengineering solution is a little bit like the Band-Aid solution to me. It's not really attacking the core of the problem, right? This sort of project involve enormous cost and enormous
The curtain
challenges.
one. Yeah.
Yes,
Right.
yes, all of them. And it's not even clear that they may work. So I think the intent of these sort of actions is good. I'm pleased to see that some people are interested to support that. Uh, I think it's more important at this point to make sure that we have the observation network that we need in these environments to really understand what's going on in more details, to understand the environment where we're living in. A lot of these places, like the cavity in front of Thwaites Glacier, we've never been there. We have no observations of what it looks like. It's very presumptuous to think that we might know exactly what's going on there without seeing it.
So this is the part past the grounding line and to the land. That part underneath that's filled with
Part where
water.
the ocean meets the glacier ice and starts melting it vigorously. It's important to be there to observe these interactions, to really understand them. We cannot model something that we don't observe.
Mm-hmm. But you haven't sent robot submarine things, or?
Well, so there's this large-scale project called ITGC, International Thwaites Glacier Project, which you probably heard about, which combined the US and the UK. It lasted about 5-6 years. They threw $50 million on it. They did get to Thwaites, not to the main trunk. They went to a part of Thwaites which we call the eastern ice shelf, which is shallower and probably not as dangerous as the main trunk, because they could not get to the main trunk. It's actually
Right.
difficult to
It's
get
blocked
there.
by the grounding line.
Yes, blocked by sea ice conditions. These places are really difficult to get to on a ship. They're very difficult to get to also if you want to land on the ice. That doesn't mean it cannot be done. We haven't necessarily put the effort at the right magnitude to do that. In 1947, Admiral Byrd launched Operation I Jump around the Antarctic. They surveyed the whole Antarctic continent. They did that in 1947. In 2025, we had a fantastic experiment with the US and the UK for $50 million for 5 years. And now we're done. It should really be the beginning of more investment in scientific observations. If we really want to understand the evolution of Thwaites, there are some observations that need to be collected on the ground that we cannot get from satellite and airborne. And until we have those, it's going to be very challenging for modelers to do anything reasonable. So that's the thing the audience needs to realize. We are being asked to predict the weather in these environments without weather stations, without observations, and that's really difficult.
That's a good way to put it. But speaking of that, actually, so you worked for JPL, and is quite famously the Trump administration is cutting back climate research left and right and dismantling climate and regular science. Has your work at JPL been impacted by that so far?
Yeah, it's been impacted. I think it's really affecting the mood of people, engineers, scientists working on this. The public needs to realize all of these scientists and engineers working on these missions really want to serve the cause of society. They're doing this to protect human populations, to protect them from climate change, from sea level rise. We need to understand the planet for that so we can manage it better. And it's disheartening to see this negativity about observations, this tendency to encourage people not to make decisions based on knowledge, but rather based on ideology.
Right.
It's not going
not going to work out too well.
Right?
If you do that.
So all of these people are good people. We really want to work to help society and protect lives, and they are being threatened. They are being shaken around right now, and it's not beneficial to anyone. I think there's a general sense in the earth science community right now that observations are being threatened, that there's a tendency for the administration in place to say we're going to collect less observations. That's really damaging, because these observations are fundamental to anyone living on this planet. We need to observe the Earth if we want to understand the environment we're living with, and make better decision on our future.
Getting back to geoengineering, because we're not reducing emissions fast enough and temperatures are really at the high end of the range of predictions.
Yes.
There's a lot of talk about doing stratospheric aerosol injection to cool the planet. And, the purpose of that really is to cool, to stop the extreme weather and get temperatures down. But one of the things it would also do is make the poles colder. Have you looked at that? Like, if we did SAI, or stratospheric aerosol injection, what impact it might have on preserving Antarctica and Greenland?
No, well, I'm not a big fan of his ideas, right? The aerosol, if you launch SO2 in the atmosphere, it comes back as acid rain. You have to do it all the time, because these aerosols are going to stay about 1 year in the stratosphere and then fall down, right? We ran an experiment on that with the help of volcano Pinatubo.
Right.
It's an experiment, and it cooled the planet by 1 degree for 1 year, and then it went away. So we have to keep blowing a volcano like Pinatubo every year to do this sort of thing. So it's the sort of magnitude of these efforts, to me, doesn't make any sense compared to reducing carbon emission using clean energy that's going to produce cleaner air, cleaner water, that provides energy resources to more people across the planet, not just those who have access to greenhouse gas, the oil, but people who have access to solar panel technology and windmills, right? Eventually, humanity proceeds sometimes in a chaotic manner, especially if we look at the news every day. We feel like it's constant chaos. But in the background of that, the voice of reason always wins, because we end up doing the right thing at some point. And the right thing is to transition our energy production to something cleaner, more sustainable, and renewable. So all these other geoengineering solution, to me, are sort of a dangerous distraction. Yes, it might be of academic interest to look at that, but in terms of practical interest, it seems to me that it's deviating our attention from the real cause of the problem. We know what causes this, right? And try to solve that, rather than trying to put a Band-Aid in the stratosphere to protect us for a little while.
But even if we did, well, first of all, 100% agreed that we should cut greenhouse gases much faster than anyone thinks is even possible. But even if we did that, which we're not doing, I mean, we're maybe slowing. Well, right now they're still at a record high, but maybe at a plateau if we're lucky. But even if we did that, it wouldn't lower temperatures. Temperatures would continue going up until we actually reach zero, if we're lucky, because the Earth itself can give off CO2 in response to the warming. And so if we did that, if that's all we did, then temperatures keep going up. We're going to definitely pass 2 degrees on our way to 2.5 and 3 degrees, even if, again, assuming we get serious about this, which we haven't done yet. And therefore, all the stuff you're working on, it's all going to happen, right? It's going to collapse. The sea level rise is going to go up. It might go up a little bit later than otherwise, maybe 20, 30 years, 50 years, but it's still all going to happen. So it's still that approach, in my opinion, of only focusing on emissions reduction, which I want as much as you do, okay?
Yeah.
But I think if we don't add to that removing carbon from the atmosphere because it's already way too high. By the way, maybe you can confirm this, but my understanding is the last time CO2 was as high as it is today, 420, parts per million, sea levels were about 75 feet higher than they are now, 20 meters or something like that.
Yes.
So it's pretty, that's pretty bad. And so we have to remove carbon. And since we're going to pass tipping points like AMOC and collapse of all this stuff, no matter what we do on reducing emissions at this point, that solar radiation management, which by the way is the cheapest of all the things we could do,
Yes.
is something that would buy us time to do the first two. So anyway, that's a whole other. We've done many programs on that here, by the way. I'm not don't mean to turn this into that. But
more optimistic than what you said. I think models tend to show now that if you curb your carbon emission, the climate will not keep warming. It will react to that more quickly than what earlier models suggested. Earlier models suggested it's going to take 30 to 40 years, and the more recent models say no, it could actually work out much faster. We've also
but to stop rising.
Yeah. So curbing greenhouse gas emission to level it off to some concentration of carbon in the atmosphere will also level off the warming. We will not keep warming.
But that's only if we're lucky, though, because Jim Hansen's latest research says that equilibrium climate sensitivity is actually 4.5 degrees, not 3 degrees, that those models that say we're leveling off assume, and that's 50% more warming for any given amount of greenhouse gases. So, as we don't know how fast the ice will collapse, we really don't know exactly what would happen. We know it'll be much better if we cut our emissions to zero.
Well,
but we don't know it's actually going to level off. We have our fingers crossed on that, really.
The state of things is such that yes, we need to curb down our greenhouse gas emission and eventually zero them. But even that may not be enough. I think that was your point, and I completely agree with you. Now, this is becoming overwhelming for the public to hear that. It's like we just don't have to wean ourselves from the carbon. We also have to clean up our act, and sequestering that carbon back in from the atmosphere into the ground is a lot more tricky than reducing our carbon emission. But eventually, we need to do that. And I don't know if we'll do it or not. I may not be alive when that happens, but
well, we're practicing now. We're looking at ideas. Some of the nature-based solutions are actually relatively inexpensive and they're not developed yet. But everyone thinks you have to build a mechanical machine to suck it out. But there are some other things you can do. Not planting trees, by the way. That good thing to plant trees, but they don't work as a long-term carbon solution. But there are other things, weathering rocks and we discussed.
For sure, we should not cut the trees in the tropical forest, and we should be worried about the tropical rainforest because it sequesters a lot of carbon.
So before we move on to questions with Other, I want to give you another chance. Can you give us a feeling for the range of sea level rise? It sounded like you're expecting 1 meter of sea level rise this century, but if things go bad after 2050 in Antarctica and Greenland, northern Greenland especially, that's the first time I've heard of that, that we could maybe see a couple of meters at the end of the century. Is that the kind of feeling?
That's the kind of feeling with large uncertainty, and also based on the fact that to exceed 2 meters by the end of the century, we really need to kick things in, and we need to kick things in tomorrow. So that's not likely. But again, we need to be careful about how much we understand about the dynamics of the system. Much of what we've observed in the past 4 years was not predicted by models, was not predicted by anyone. It went much faster. So we have to remain cautious. So we're on course for 1 meter. It could go as bad as 2 meters. To go beyond that would be quite extraordinary, to be honest. I could not quite put my finger on what could cause a sea level rise of 2 meters by 2100, more than 2 meters.
So, and speaking of that in general, just bringing Jim Hansen back into it, he wrote a paper in 2007 called Scientific Reticence and Sea Level Rise, where he just said that scientists in general have, they err on the side of least drama. There were a bunch of reasons. Like, as you said yourself, you have to be really quite sure before you're going to publish something, right? You really want to be sure. So they they say it's going to, well, back then it's going to be 2 feet, even though they realized it could be like 6 feet, but they only talked about 2 feet because that was all they could be sure about. And
Yes.
that's not really what you want to hear. You want to hear the part that they're not sure about. If it's 25% chance it's going to be 2 meters, you want to know that and act on that, right? That's very, very risky. Do you have a feel for it? Just now, a general thing about how conservative scientists working on ice sheets, sea level rise are being, in that sense, being reticent to publish the worst case stuff?
The scientific community is sort of conservative by design,
right?
Because the voice of the scientific community is kind of the average of what is being said on that topic among all of them. So if you have some extreme view one way or another, it's going to be averaged out. To sort of reach a consensus that West Antarctica is collapsing, even that, there's not broadside agreement on that. There are people who are still on the fence with that, and that's okay, that's respectable. The way science works is that we pile observations, evidence, modeling, independent lines of reasoning until we feel a little bit more sure about something.
Right.
And until we feel sure, scientists are sort of reluctant to say we think this is the right answer. This is what research is about. You make progress along the way, and at some point you reach some conclusion. You can call it a theory at that point. Everybody agrees, right? It's been proven again and again and again, and that process can take a long time. It's not going to happen from one year to the next. The time scale of that is more like 10, 20, 30 years for the community to embrace the concept. So, and there's also a sense, especially in the polar science community, that we have a little bit of responsibility on what we say. You don't want to scare off people and then later on come back and say, oopsie, no, it's actually not working exactly like that. We made a mistake.
No, that's what he was pointing out, that the avoidance of that, however, leads to potential underestimating of the true threat, right?
Well, so I think it's good to balance observations and model also with the opinions of experts. We're really working on this intensively. They are the people looking at the latest data. They are well aware of the field, and they may have an opinion on how things are evolving based on their understanding of physics, based on the collective data set of observations that may be a little bit ahead of what the scientific community as a whole is thinking. Okay. So it's good to balance that out in sort of formulating the level of concern you should have about climate change.
Okay, well, thank you. And by the way, we're gonna go on to some other questions from others here. Yes. I really want to thank you for all the work you've been doing. As I said, I've been following it for a long time. It's some of the most important work in the world that many people haven't heard of. So I'm really glad you're on today to talk about it. And now we're going to bring on co-host Leon Simons, who has a question. Let's bring Leon on here. Whoops,
hi there.
I'm the wrong.
Hi, Leon.
There we go.
Hi. Hi, thank you for coming on Climate Chat. Let me share some, I think this is what you were talking about. So I want to show people this great image of Antarctica without ice and showing the, so I think, can I show it here? Thwaite is about here, right?
That's right.
Yeah. So,
and everything blue in that map, blue and white, is below sea level. Everything about sea level is color-coded green and brown.
But it's all covered by ice.
It's called covered by ice, and you see that if you melt the ice, the West Antarctic will be reduced to an archipelago, and there'll be a lot of left in East Antarctica, but you see a lot of blue in East Antarctica. We haven't talked about this today, but I am also very worried about that part of Antarctica. That's 12 meters of sea level rise, right where you move your little arrow.
12 meters?
Yes, that's 12 meters, that big sector.
Whoa. And this combined, you said like 1 meter plus 2 meters from here, but combined West Antarctica is 4
West
meters?
Antarctica is 3 meters of sea level rise from marine ice sheet instability.
Okay, and then the other ice on land is another meter, more or less.
Yeah, so East Antarctica is not changing as fast, but is a concern.
Yeah, yeah, it's clear from this as well. I think this is your data, maybe your graph as well, or your map as well, where you can see that the more red it is, the faster it is.
Yes.
Melting.
So, Leon, what your question there?
Yeah, my question was, I thought this was a really interesting study where they showed that during the glacial, the Eemian, there was migration from octopus, this certain type of octopus, from the one part of the ice sheet to the other part of the ice sheet, and they concluded that most of this ice had melted, and of course during the Eemian, sea levels were about 7.5 meters higher.
Yes.
And my question was, like, what can you learn from other scientific fields, especially like this field where you look at more biological fingerprints, which we wouldn't expect to learn much from in glaciology.
That's right. So that's what I was referring to in that conversation we've done before. Scientists build contingencies based on multiple lines of evidence. Right? So you may have some seafloor coring that says this part of West Antarctica was melted away in the last Eemian, and now we have another line of evidence from marine biology that says yes, we find the same thing. So that's sort of the thing that you like to have in science when you have these multiple lines of evidence from different parts of the system pointing out to the same thing. That part of West Antarctica melted away in the last Eemian, which was maybe half a degree warmer than today or something like that. We're not quite sure how much warmer it was. We're probably very close. And sea level,
about 1.5 above pre-industrial.
Yeah, and sea level was 6 to 9 meters above present. And you can't get 9 meters by just melting Greenland. That's 3 meters. You need some big signal from the Antarctic, and West Antarctica is one. And I do think that there is some part of East Antarctica that went down too, but we're not sure which one.
Okay.
Thanks.
You have another question, Leon?
Yeah, so 2 more short questions. This one I think is quite interesting. It's on tipping points, this graph, and here's West Antarctic ice sheet. And the question I have for you is, do you think we've now reached a point where the West Antarctic ice sheet will collapse? Can we still reverse it, even if we would stabilize temperatures at current levels?
It sort of depends what you mean by collapse.
What do you mean by collapse?
Yeah, what do you mean by collapse? I think to the general public, collapse is like a big building falling down to the ground, right? And so once it starts falling down to the ground, you're not going to stop that. For me, the collapse of an ice sheet is more a sort of forcing from the climate that makes it so that the ice will keep retreating in that environment. If we stay in that climate regime, there's just no way that ice will stop retreating. We already passed the point of no return. It will keep retreating until all the ice is gone. So I think we reached that in the West Antarctic, unless we can come back to a climate that we had in the 80s or even earlier. And the same probably applies to North Greenland. So I don't necessarily like this tipping point threshold because it gives the false sense that we haven't reached that threshold yet, so we're fine. I think for the ice sheets, we already crossed that threshold. But in my opinion, that doesn't mean that this is Doomsday Glacier. We already pressed the button, it's going to go down no matter what. I don't think it works like that. I think that if we are able to change the course of the climate warming, and I don't know exactly what that means, but 1.5 degrees is a bit illusory. We're already there. 2 degrees may be a good shot, but we just don't want to keep it warming anymore. We already are pushing the climate in a bad state. The collapse of these ice sheets could be slowed down. It will still retreat, but it will retreat at a much slower rate, which is what we want. We just don't want this thing to change too quickly. So if they retreat in 400 years instead of the next 50 years, that's fine. We are okay with that. In 400 years, civilization on this planet will be totally different, even in 100 years.
If it exists, but that's a whole other thing.
Well, that's another story.
Okay, Leon, your last question?
Yes. Sorry, I was playing some. Did you? I learned about this 6 million year old ice, and I was wondering if you know when we can what we can learn from that.
Well, the big deal about this more than 1 million year ice is to figure out why the pacing of the glacial cycle changed a million years ago. It has to do somehow with the cycle of the carbon. I don't know necessarily that this will have drastic implications for what's happening today on the planet, but it will tell us a little bit. I mean, something fundamental changed on the planet, the cycling of the ice ages a million years ago. It would be of use to understand why that's happened. And that's what this research is trying to answer.
Yeah. Do you know if we can see the CO2 concentration from back then, or you don't know? I think it's a different field. If we can learn what the CO2 or the methane concentrations were back then, do you know if they can find these air bubbles like they can from the past 800,000 years?
So the challenge of this million year ice is you have to go really deep under the ice, or now they're also exploring the concept of looking at ice that was in the bed, and as it moved towards the coastline, kind of made its way over obstacles and comes at the surface. But then you have to untangle everything, that ice has been deformed and transiting. So there's a lot of exciting science that will come out of it. It's not my field of study, but I'm excited to hear more about this in the coming years.
Great. Well, thank you, Leon. And now we're going to move on to Stacy. Stacy, hi.
Hi. Hi. Hey, Dan. Hey, Eric. Thanks for being here. And I just wanted to do the thing we never do, which is tell people to please like this program and subscribe so that more people can hear this important message. I have 2 quick questions. Eric, have you read The Ministry of the Future? And if so, did you find it accurate?
Ministry of the Future? No.
Oh, I highly recommend it. It's a science fiction, but it seems very true to life on other climate matters. So the way they were talking about addressing thwaites and other problems in the Antarctic, I don't know. You'll have to get back to us about that.
Okay.
And then the other is, given the current political climate in the U.S. and the anti-science movement out of it, have you considered returning to France?
That's a great question. The short answer is no. I still remain confident that the U.S. is supporting science. The U.S. has a history of supporting science, and it's apolitical. Because developing science and technology is a benefit for society. There's a lot of economic return from investing in science and technology. So I cannot conceive that this country will fade away from science. There may be a bad vibe right now, but it's just a bad vibe. It's not necessarily something that makes sense. So I hope we're going to sort of get out of this bad vibe, which is probably not supported by the entire nation. It's supported by an administration with a certain agenda, but that agenda may change. I think it's kind of really scary to think that society could decide to move away from scientific knowledge. It's
Especially in
almost
this time.
you want to tell these people, are you serious? Do you want to govern based on ideology rather than knowledge? I'm sorry. I think for my family, for my friends, I want to make decisions based on knowledge.
I agree with that. So, Stacy,
One would
we'll be
hope.
back with you for some
Yeah.
YouTube comments in a moment, and then quickly go to a question from Eli. Eli, are you there?
Yeah,
Hi,
thanks,
welcome.
Dan. So when people think of West Antarctic ice sheet collapse, they tend to think of sea level rise, coastal flooding, perhaps sea ice loss. But the resulting ocean stratification would affect the ocean CO2 sink, nutrient upwelling, the biological carbon pump, deep water oxygenation. Literally sea life could suffocate, as well as shifting loading on methane clathrate deposits. Do you think all of these associated risks are fully appreciated by the general public?
Oh, that's a great question. I completely agree with you. The short answer is no. There's not enough attention paid, especially to the dynamics of the Southern Ocean. Now, let's take a perspective back on that. The Antarctic research is not even 100 years old. 100 years ago, people were trying to get there and come back. So Antarctic science is still very young. There's still a lot of things we've never observed and measured in the Antarctic environment. Yet it seems very remote from our lives. It's very remote from us. You can also ask the public, where's Antarctica on the map? They may be hesitant to figure out where is Antarctica, but it is quite relevant to the whole climate system. It's very relevant to the thermoline circulation, to marine biology. It is impacting the rest of the planet. You're absolutely right. And I'm a little bit concerned that our sort of observation network of the Southern Ocean is not up to scale for that, is not up to par for us to fully understand the ramifications, such as what you just mentioned. Because it's a little bit difficult to get there, but also because there's not a full appreciation on how change in the Antarctic could impact not only Antarctica, but all of us on the planet. And that's sort of lacking. Antarctica is remote, but it's relevant to us. In fact, a good example of that, it's the same for Greenland. If Antarctica melts, sea level around the Antarctic is not going to rise. It's actually going to lower. It's going to rise far away from the Antarctic rather than around the Antarctic itself. Because if you remove ice from the Antarctic, the continent will rise. Right. So that's another example of what's happening to the Antarctic is relevant to us. And in that context, I wish there was a little bit more efforts, a growth in the community of researchers working in this environment, because what is at stake is so important. We should invest more, and whatever more we invest on it will certainly pay itself back by providing more information on the changes in the planet to make appropriate decisions.
Okay. 1 second here. Thanks, Eli. Appreciate that. And back to Stacy for, do you have any? I saw one.
I have a couple. Yeah.
Okay, go ahead.
The one which piggybacks onto my "Are you going back to France?" Wolf wants to know where you'll retire to.
We're diverting here.
I think so. Yeah.
I don't know. Like some of my friends said, I feel a little bit like a citizen of the world. I live in this country. I'm an American citizen and a French citizen, but I don't necessarily carry my French flag or my American flag around. I'm a citizen of the world. I told you I don't think I would go back to France because I think the research world is more supported in the US than it is in France, unfortunately.
Wow.
There are more opportunities for scientific research in the US than in France at the moment. In terms of retirement, well, that depends on where my family members are, but I hope I'll stay movable and spend some of my time in the US, some of my time in Europe when I retire. But I'm not even thinking about retirement yet, Stacy. So,
Well, I
Anyway,
think they were thinking where you avoiding sea level rise that seems
oh,
imminent.
well, let's
well,
move on to something a little more technical here.
Yeah.
I don't know the answer to this one. Can Eric explain the difference between marine ice sheet instability versus
yes.
marine ice cliff instability in a runaway scenario, but or not?
Yeah, Mickey is a physical process that has been put together by a number of colleagues, Pollard, DeConto, Richard Alley, uh, by which a calving cliff at the end of a glacier terminating in the ocean could become unstable because of a hydrofracture, there's water filling the cracks, or because the cliff is too high and then the ice cannot support all that stress and it's going to break up. It's a brittle fracture. And when they parameterize this marine ice cliff instability, which is called instability because once you start that process, it could propagate inland and go into deeper ice and not stop.
Mm-hmm.
When they put this physical process in models, DeConto and Pollard were able to replicate some of the rapid rates of sea level that we've seen in the past, which was good because the other models were not able to do that. But they may have gotten the right answer for the wrong reason. Right now, the evidence for Mickey, the sort of observational evidence, is lacking. And personally, until I've seen evidence of marine ice cliff instability on glaciers on Earth right now, I will be a little bit suspicious that it's a nice concept, but it's not a real one. The marine ice sheet instability is a well-proven concept. It's solid in terms of the theory, in terms of observations, and it's not just Greenland and Antarctica, it's also the Alaska glaciers. It's a very solid record. Mickey could be an additional process of ice sheet collapse on top of that. But as of now, I think the evidence for that existing is not strong enough. And moreover, I am not sure we need Mickey to really collapse these ice sheets at the rate that they've done in the past. I think the Mizy Mickey, they sound like the Yeti in the Himalaya, like a big monster. Mizy is an important one. The marine ice cliff instability is a concept that still needs more study to see if it's real or not.
Okay. Good. And Stacy, do you have another question?
Yeah.
I think just maybe one more.
Tom said, why do climate scientists love the 1,000-year timeline for climate predictions? Why do they hesitate to extrapolate beyond prehistoric eras of warming when we emit carbon rate today at a rate of 30 times?
I'm not sure.
Well, climate models, they like the several century time scale because when you create a change in climate forcing, you want to give enough time for the system to respond and get to the end state, right? You want to know to what state is this climate, is the Earth going to evolve, and you need to wait long enough for that. What makes me a little bit hesitant about caring about the end state is that the projection of 1 or 2 centuries or 3 centuries are going to be relevant to a society that's going to be so different from what we have today that I don't care to project the future in 200-300 years. I want to know what's going to happen in the next decades, in the next 50 years, because that's what's going to affect us.
That's what we care about now. Yeah.
In 100 years, who knows? Maybe people will say, "Oh, we are totally in control of our carbon concentration in the atmosphere." In the old days, we didn't know how to do that, but now we know. Now we know how to do that.
Okay. So there's lots of unknowns, but a lot of excitement. I guess it's safe to say there will be a lot of exciting new information research on Antarctica and Greenland in the next coming decades, if not years, by the way. So you'll have a very exciting job for continuing future. And Eric, I want to thank you again for all the work you've done up till now. It's super important and something that we need to know more about. And thank you for spending the time to communicate it to our audience and beyond here. And by the way, congratulations on some of the awards. I didn't have a chance to read all the awards you've gotten for your research, National Academy of Science, and all these kinds of things. But you gave a really good talk that I watched the other day when your acceptance speech at the National Academy of Science. So everyone can find that. And there, by the way, links in the description to your homepage at UC Irvine, JPL. So they can, and Google Scholar. So I put that in there so they can see your research as well. So again, thank you for everything you've done. Thank you for joining us today. And everyone, thank you for joining us for this episode of Climate Chat. And we will see you next time.